Hey, fellow mathers. Before we get into this episode, we want to share with you how you can get access to free content, professional learning that will keep your students engaged and doing the math that matters. Get ready to go to this link, mathisfigureoutable.com/challenge.
That's right. Registration is open for the free Math is Figureoutable Challenge that's starting May 15th and runs to the 17th at 7 p.m. Central. We're going to have 3 nights jam-packed with learning and routines that you can take straight to your classroom.
In these challenges, we have a great time. We do some math, talk about classroom experiences, give away super cool bonuses and prizes. You won't just walk away with routines that are naturally engaging and encourage your students to think mathematically. You'll also have a chance to win over $6,000 worth in prizes, including a few virtual PD sessions for your school. I'll be joined by my wonderful co-host Kim and special guest Jenna Labe.
You can register at mathisfigureoutable.com/challenge for a fantastic learning experience. That's mathisfigureoutable.com/challenge. Now on to the show.
Hey, fellow mathematicians, welcome to the podcast where math is figure-outable. I'm Pam.
And I'm Kim.
And you found a place where math is not about memorizing and mimicking, where you're waiting to be told or shown what to do. But y'all, it's about making sense of problems, noticing patterns, and reasoning using mathematical relationships. We can actually mentor students to think and reason like mathematicians. Not only are algorithms really not helpful in teaching mathematics, but rotely repeating steps actually keep students from being the mathematicians they can be.
I'm super excited because it's December 19th.
That is the best
I'm
time.
excited. And you have a birthday not too long.
I do have a
Christmas,
birthday
amazing.
coming up. It's
Yeah.
true. The whole world celebrates my birthday. Yeah. I mean, really. In fact, I was just talking to some people the other day, and the gal said, my birthday's on the 31st, December 31st.
Mm-hmm.
And she said, my sister's birthday's on the 30th. And I looked at her and I was like, stinks to be her. Because on the 30th, people are just getting over like all the things that were happening before that, right? And then New Year's is the next day. So nobody's going to have a party on the 30th.
Yeah.
But the entire world celebrates New Year's Eve. So there's always a party. You can always find a party. And I just pretend that everyone's celebrating my birthday, and it works great. It's fantastic.
I know several December 31st birthdays.
Do you?
It's wild. I do. Huh?
Okay. Well, we're all cool, I hope.
Mm-hmm. All right. I got another review for you. I won't do
nice.
this I won't do it every week, but
okay, not every week.
But it's
hey,
our podcast, so I want to.
And it's been kind of fun. It's fun because you check them more often than I do. Yeah.
Yeah, for
all right,
sure.
what do you got?
Okay, Kendra 619 says, I love listening to Pam and Kim every week. I teach 5th grade math, and each podcast, good heavens.
You can do it.
I love listening to Pam and Kim every week. I teach 5th grade math, and each podcast teaches me something new. Pam and Kim are so relatable and definitely help me make math more figure-outable for my students. I have recommended your podcast to anyone who will listen.
Aw.
Thanks, Kendra.
Yeah, thanks, Kendra. Appreciate that. Thanks for the recommendation. Thanks for helping us spread the word. And definitely thanks for teaching your 5th grade kids so well. That's excellent. Yeah,
awesome.
Nicely done. Cool.
All right.
Thanks for the ratings and the reviews, everybody. We appreciate it.
All right. We talked integer addition last week.
Yes.
So it's time to turn our attention to subtraction today. So listen, there's lots to do, as you know. So we're acknowledging up front, listeners, that we're just starting the conversation. Yep. You'll have to let us know if you want more.
Yeah, absolutely.
You will. We know. We'll put it in somewhere.
Hey, and before we started recording, Kim reminded me that last week we had promised that we would also talk about integer chips.
Absolutely.
So I'm going to maybe start there today. So what do I think about integer chips? I think integer chips are
colorful.
So what do I mean? There are those round things.
Yep.
There's red on one side, yellow on one side. And teachers often use them to help students kind of think about zero pairs. And they model some stuff with integer operations using integer chips. I'm just going to flat out say, I think you can do without them. So are they bad? No. Are they wrong? No. Are they super duper duper helpful? Nah. They're helpful, but are they helpful enough? So I'll just give you a quick, for instance, when we were at NCTM, NCSM, I'm sorry, I don't remember who you were. Whoever you were, you made me think. I just don't remember I was having that conversation with. Said, integer chips, like Pam, like this problem. And we did a couple of problems. She goes, they're so important because, and then we did a subtracting and negative. And she subtracted a negative incorrectly because she used the integer chip model and couldn't quite think about how, because it's insane to subtract a negative. I know right now people are thinking, Pam, I can clearly tell you how to do it. Yes, you can. You can clearly tell me how to subtract a negative using integer chips, but it's not very intuitive, and it's not very, what is a good word? It's
I mean, I
not
got
the
words
thing.
for it.
You get words. It's
It's
not.
procedural.
Well, it's not the thing that I'm going to pull up in my head when I'm doing
Right.
integers later.
Right.
And what were you going to say? What did you
I
say?
said it's procedural and it's one at a time, which
Super procedural, and I had to tell, like, hardly anybody comes up with how you can model subtracting a negative with integer
right.
chips. I know there's a few of you out there thinking, no, it was super easy for me. It's not for everyone else. Can we just it's just not very intuitive. So
Mhm.
I think we can get more mileage out of a model that we're going to use more often. So if
Mhm.
you want to do integer chips, I'm not going to tell you not to, but I am going to say maybe don't spend too much time there. Maybe get out of there.
Mhm.
Why not? What's a pitfall of integer chips? So quickly, I'm already spending a little more time on this than I was intended. So quickly, a pitfall of integer chips. Definitely subtracting a negative, but also the counting that happens.
Mhm.
If
Oh,
I
I jumped your
say,
gun. Sorry.
no, it's okay. If I say you're going to do something like 6 plus negative 7, show me with integer chips. Well, most kids can think about 6 plus negative 7,
Mhm.
especially if you're just thinking on a number line, not actually even drawing the number line, but just thinking on a number line, especially if you do it in a context. But if I make you do it with a model, now you've got to count out those 6 positive integer chips. And then you have to count out those 7 negative integer chips. And then you line them up so that you've got the 6 negatives and positives that cancel to zero pair, or I shouldn't say cancel, cut myself, that add to zero. Those zero pairs add to zero, and you've got one left over. And what color was it? Okay, it was negative. Notice that when you have that one left over, you're kind of almost reading off the answer.
Yeah.
You're doing less reasoning, and you're doing more. I do this, I do that I read off the answer. If you read off the answer, thank you, Kathy Fosno, for this. If you read off the answer, you were probably following a procedure and you weren't involved in the relationships. You weren't mathing. Too much counting, too much reading off the answer. Those are my reasons for de-emphasizing integer chips. Now, notice I didn't just say you could do them all, but if it was me, I wouldn't. I don't think it's worth it. I think we can get the bang for the buck doing other things, like modeling things on an open number line. And you might be like, well, Pam, you're gonna have to do stuff on an open number line. Yes, but that model lives on. That model, we need open number lines through calculus, right? We just put two of them together and now we have a coordinate axis. So open number lines are super helpful. We need kids, what's the word? Fluent on number lines. That's super important. Okay. So, Kim, if we were going to think about subtraction at all,
Yeah.
we have some episodes that we have talked about before for whole numbers where we have talked about that there are two main ways to think about subtraction.
Mhm.
So if you are listening to this podcast right now and that doesn't ring for you, you're like, what do you mean two different ways of looking at subtraction? Well, we can look at subtraction as the difference between the two numbers in the subtraction problem. We can also look at it as removing the one number from the first number, the second number from the first number in a subtraction problem. Most often, especially if kids have been drilled in a traditional subtraction algorithm, kids are always thinking about minus, subtracting, removal. They're only using that one meaning of subtraction. They're not thinking about that we can consider subtraction as the difference between two numbers. That often comes to bite us when we're doing comparison problems because we say, look, it's a subtraction problem. And they're like, no, this is a comparison problem, because they haven't ever thought about that we can label comparison, how far apart numbers are, as subtraction. So if that's new to you, maybe we recommend that you go, we'll put the podcast episodes in the show notes, go check, or just go search, y'all just look, Math is Variable podcast subtraction, and check out the ones where we talk about the two meanings of subtraction, difference and removal, because we're going to need both of them when we subtract integers. Okay. So to be clear, we're not going to develop difference versus removal right now. You need to have had some background there for us to use it here. Let me just say, maybe when we just filmed Kim, we often film us doing problem strings or expert teachers doing problem strings. In fact, I'm so excited that we have some new teachers we're going to film coming up soon.
I am excited too.
We film these expert teachers in real classrooms with real students You always tease me. It's not fake students. They're real students. I don't know
I
why I
do.
say real students. I know. So where we do problem strings, and then we put those problem strings, we have a couple out on the website that anybody can view. And then we put every month, we put a new one in our journey program.
Yep.
So you can see it happening with real kids. And my goal is to build up this bank of problem strings where like teachers can go look at tons of different things being taught using problem strings with kids across the grade bands. When I did that, when I went into a 6th grade classroom not too long ago, and we filmed subtraction of integers. Well, we filmed a bunch of integer stuff, and subtraction was one of them. The first day that I went in, I did a problem strings with kids with whole numbers where we talked about difference and removal. And I got them thinking about how we can view subtraction as difference, and we can view it as subtract minus take away removal. And so that was kind of a starting place for kids. And then the cameras came in the next day, and then we dove into integer stuff. So I practice what I preach. We give kids kind of that sort of sense. If you don't have that sense, go check out a podcast on it. We'll put that episode in the show notes. Come on back and let's talk about subtracting integers. Mm-hmm. All right. So Kim, let's do a quick problem string to get at integer subtraction.
I was almost a really smart aleck.
You were going to be smart. You were going to be smart aleck?
Was.
Kim, you're never smart alecky. Not. What's the opposite of that? You're always smart alecky? I don't know if you're always smart alecky. I wouldn't say there's a day that doesn't go by where
Is there
you're
a difference between snarky and smart aleck? Oh. I feel like smart aleck is probably negative. Let's not be that.
Okay, let's not be that. You are snarky. That's true.
For sure.
So you're saying snarky's positive?
I don't know. Probably not to anybody but me. Witty.
You like being snarky.
I do. Mm-hmm. All right, moving on. I'll do the
Sometimes I'll meet people and I'll go, "Oh, Kim, you'll like them. They're snarky."
You do.
She instantly lights up. She's like, "Oh yeah, I want to meet that person." So everyone who's not smarky, Kim, smarky. Everyone who's not snarky, Kim will also like you. Yeah, she'll like you as well. She just is pretty confident she'll like you if you're okay. Moving on. Goodness gracious, neither of us got sleep last night. Moving on.
I know lots. It's because we're busy, but we love it.
Okay, if I were to ask you, Kim. Now the cadence in this problem string is going to be very important. So maybe help me a little bit because I'm going to spend some time talking about a problem, but not because I would with kids. I'm going to talk about why it's the problem there. So listeners,
should we do the problem string or do you need to talk about
and then back up?
Yeah,
I can try.
Okay, well, it's okay if you can't.
You know I'm bad at that.
I know. Well, that's why I maybe thought I wondered if you could.
You know, it's interesting, podcast listeners. When Kim and I present together. I'm often the example of a string with lots of teacher talk all the way through it. And Kim is the example of a problem string that goes straight through, you do it. And then she backs up and does let's talk about why I did what I did. So for that reason, we're good. We work well together. I have gotten better at doing some.
You have.
Yeah. I'm better when someone times me. If I say time me, then I'm kind of, I don't know, somehow that tells my brain to not stop and do teacher talk. Let me see. Let's see if we can do it. Okay. So, Kim, what is 5 minus 3?
Oh, 2.
And I know that's not hard. We're not going to pause very long here, 2. I'm just going to make a quick picture of your thinking just so we can kind of refer to it after. You didn't have to think about that. But I'm just going to say, can we think about 5 minus 3 as 5 subtract 3? We can. But can we also think about it as the difference between 3 and 5? We've done some work with that. So on the board, I would put 3 on a number line. I would put 5 to the right of it. I would draw a little jump above it and put 2. And you're saying the difference between 3 and 5 is 2. Cool. Yep. Next problem. What about 3 subtract 5?
-2.
And how do you know?
For this one, I started at 3 and go back 5.
And if you do that, you kind of skip over the 0.
Yeah.
And you kind of landed on -2. So I've now written on the board 3 minus 5 is -2. And I'm going to pull out of Kim. I think I have to talk about it as we go. I don't think it'll make sense if I don't.
Yeah.
So I'm going to pull out of kids that -2, not 2, and then I'm going to say, could you reason about that with elevation? So Kim, can you reason about that with elevation?
So I'm at 3 feet above sea level and I drop 5 feet. So I'm at -2 feet.
Which
2 feet below sea level.
There you go. Okay, cool. And how about temperature? Can you reason that with temperature?
Yeah, it's 3 degrees and it drops 5. And so it's really cold, -2 degrees.
Brr. And can you do football?
Ugh.
No, you don't have to do football. Football's kind of
I'm 3 yards ahead of the line of scrimmage and I get pushed back 5 yards.
Nice. And so where are you?
I'm 2 yards behind the line of scrimmage. -2.
Bummer. We're back. That's terrible. And what about what am I leaving out?
Money.
Debt. Yeah,
Yeah.
money.
I have $3. I owe someone 5. So I'm in debt to -2.
Cool. All right. So then I'm going to say, hey, I'm a little curious because we just said on the first problem, 5 minus 3, that we could think about that as the difference between two numbers. But
Mhm.
every scenario you just told me about, you were kind of falling. The temperature was falling 5 degrees. You
Mhm.
were going down below sea level. It was removing. You were going in debt, like removing money from you. What did I leave out? Debt, elevation, falling. Football, you were being pushed back 5 yards. All of those were kind of a subtraction removal context. Could we look at the difference between 3 and 5? Could we let the subtraction, because right now I'm pointing at the subtraction symbol, 3 minus 5. I'm pointing at that subtraction in between the numbers. And I'm saying, if that means difference, that's what we've said.
Mhm.
We said with whole numbers, it can be difference. Then I should also be able to look at the difference between 3 and 5.
Sure.
But the distance is 2. But you just told me
Mhm.
the answer was -2. Ah, crumb. I guess we can't use distance to think
Mhm.
about subtraction.
Mhm.
Or can we? So I would have, for both problems right now, I only have one number line on the board. We talked through those other contexts when you were removing
Mhm.
3 minus 5, but I've really only got the one number line, and that is from 3 to 5 is this distance of 2. And
Mhm.
so I'm going to say, could we use distance? Could we find out how far apart the numbers are? But then think about removal to say, yeah, they're 2 apart, but is it going to be +2 or -2?
Mhm.
The distance is 2, but
Mhm.
from 3 feet, you fell down 5 feet. Where are you? Yeah,
Mhm.
you're 2 feet below sea level. From 3 degrees, you fell. So we can actually use distance to find out the magnitude of the answer, the absolute value of the answer. But then we
Mhm.
have to use removal to decide, is it going to be positive or negative? I wonder if that will work. Let's try another problem. So, Kim, what if I said 7 subtract -2?
Mhm. I just drew a number line and I
Okay.
put -2. And then I also put 7. And so I
Where
found
are they? Can you orient us? Because nobody can
-2.
see.
Yeah. So -2 would be to the left of 0. I didn't
Mhm,
have a 0, but I'll put it right now. So -2 is to the left of 0.
mhm,
And then 7 is to the right of 0.
mhm.
So the space between those is 9 units, 9, whatever.
Okay. Because
And so
I've got that -2 to 0, I've got the 0 to
Mhm.
7, you add those together, you got
Mhm.
this so 7 and -2 are 9 apart, okay?
Mhm.
Okay.
Yeah.
Uh-huh.
And so the way I think about it is I ask myself if it's going to be positive or negative by thinking about the context. So if I'm at, I have $7. No, I don't
Mm,
actually do. I,
yeah, this
I
is
think I
tricky.
think about if I remove a number that is smaller or larger. Like, am I removing something that is less than what I had, or am I removing something more than what I had?
Well, and let's pause for just a second and look
Yeah.
at the first 2 problems that we did,
Yeah.
because we had 5 minus 3 was 2, and 3 minus 5 was -2. So you just kind of said bigger, smaller numbers, and this is exactly what we're going to do with kids. We're going to kind of dive in. How did you know the distance between 5 and 3 and 3 and 5 was 2? What was the size of numbers involved?
Yeah.
Your whole life up until we started bringing in integers, like when you were subtracting in grade 2.
Mhm.
I've been talking to Canadians lately. Can you tell? In second grade, where was the big number? Where was the small number in most of the problems you were ever subtracting?
You were always subtracting the smaller number.
Yeah. So from a big number, you were subtracting something smaller than it, then you would get a positive answer, right? Like if you had money and you subtracted just a little bit of money, you still had money. If you were above sea level and you fell down just a little bit, you were still above sea level. If the temperature was whatever and it dropped just a tiny bit, like you're not close to zero, so just drop less than getting you to zero, then you're still above zero.
Mhm.
So all of those contexts help us think about, if from the first number you just subtract something smaller than it, bam, the answer's positive.
Mhm.
But what happened in that 3 minus 5? How does that
No, you're
go ahead.
subtracting the bigger number now.
Yeah, so from 3, you're subtracting something bigger than it. Oh, from $3, I'm spending 5. I'm in debt. From 3 feet above sea level, I'm falling down 5. I'm 2 feet below sea level. From 3, context, sea level, temperature. From 3 degrees, the temperature dropped 5 degrees, I'm below 2 degrees. All of those contexts help me think about from a number. If I subtract something bigger than it, the answer's got to be negative. So what does that mean for 7 and -2? From 7.
Sorry, you're asking me.
Yeah. Sorry.
So I think about those as from 7,
Mm-hmm.
I'm subtracting a number smaller than it. So then my answer is going to be positive.
And that is the clincher of comparing those numbers. From 7, are you subtracting? So as I've written on my paper, I have 7 subtract, and I wrote in parentheses -2. So from 7, you're subtracting something smaller than 7. So you actually have to get kind of in your head, how are 7 and -2 related? So -2 is smaller. They're 9 apart. Since it's smaller, I'm removing something smaller. That's like what I've done since 2nd grade. Bam, the answer is going to be positive. Cool. Well, so then what if I just turned that problem around on you and said, same numbers, -2, subtract 7.
Yeah.
So same difference, right? Same distance between the numbers. Okay,
But this time I'm starting at -2 and I'm subtracting something larger than what I have. So it's going to be what did I say? -9.
-9. The distance is 9, but we're removing something bigger than we started with. Bam, the answer has to be negative. So this is not trivial. Like we have to, let's see what happens in another problem. So then I might say to kids, okay, what if I start at -5 and I'm going to subtract -3, -5, subtract -3. Whew. How are you thinking about that?
So I wrote down -3 and -5 on a number line.
Yeah. And how do they relate? Which one's which?
It's a good question. So the -5 is to the left of the -3. Because -5 is bigger than -3. I stood on my paper. -5 is bigger than -3.
Ooh, careful. -5. It's a bigger debt.
Oh yeah, it's bigger debt, so it's smaller.
But we'd actually say it's smaller. Yeah, that's super tricky. So as you go to the left,
what did I say?
You said -5 was bigger than -3.
Oh, it's smaller than -3.
Okay, all right, just checking. Well, hey, and maybe you meant to say that or not, but lots of this is a thing that as you deal with negatives and positives, sometimes we have to stop ourselves and just think, okay, wait, what does that mean? It is a bigger debt, that's confusing, right?
Yep.
I tell you, Kim, when I used to do limits in calculus, I would say, as you go to the right and X is getting bigger, well, that's true as you go to the right. And then I would say, as you're going to the left and X is getting bigger in the negative direction, I had some very nice people. Thanks, Diane McGowan and Susan May, who were like, you cannot say bigger negatives. And I was like, why not? And they're like, no, those numbers are smaller. I was like, So I had to really work on that. Okay. So I've got -5 and -3 on my paper, kind of like you said. -5's to the left, the -3's to the right. Okay.
So the distance between those is 2.
Okay.
But because I'm subtracting something larger than what I currently have, it's -2.
Because -3 is larger, and it's the problem was -5 subtract -3, -5 subtract something larger than it. You're like, the answer has to be +2.
Yep.
Okay. So what if we flip those around? What if it was -3 subtract? Sorry.
Did you say it was positive? The answer is +2? I think you just said +2.
I did, but I should have said -2, huh?
Yeah.
I don't know why I said negative. Okay, because you're subtracting anything bigger than it, it should be negative.
Yeah.
Right. And maybe I'll stay in context to help me make sense of that. If I've got some money, but I spend more than I had, I'm in debt. If I'm at sea level and I drop more than I was, through the 0, then I'm negative. If the temperature is, whatever, but I drop more than that, then I'm below 0. Yep. Okay, cool. Thanks for that.
Yep.
All right. So now we're flipping it around. -3 subtract -5.
Yep. So they're still the same distance apart. -3 is
same
still
number
2
line.
away from -5. Yep.
Yeah, still 2 apart. Okay.
But this time I am subtracting less than what I had.
Can you give me a context where you're making sense? Then does that mean it's positive or negative? If you subtract, if -5 is less than -3, and you're subtracting something less than you started with.
If I was at -5, Oh, no.
So don't do too numbery. Just like
I'm subtracting. I have more debt than I started with.
I have to think for a second. -3 and -5. So from -3,
Mm-hmm.
you're subtracting something less than it. So you
Mm-hmm.
have some money, you're subtracting less than that.
Yeah. You can correct me if I'm wrong, but I feel
Oh, go ahead.
like the challenge when you are subtracting negatives is that we try to stay in context too much.
Yes, I will concur. Yeah,
Okay.
which is why I just said try not to actually use the -3 and
Yeah.
-5.
So
Be a little more general. Uh-huh.
I think we do a really good job, or we attempt to do a really good job, really having kids understand negative numbers in context
Mhm.
and what does it mean to have negative numbers. And then we rely on their understanding of where numbers fall on a number line, that -5 is, and where -3 is, and how they relate to each other, so that we can use those intuitions when we get to something funky like subtracting a negative.
Yeah, because subtracting a negative doesn't work well in context.
Yeah.
It
Yeah.
just doesn't. And people try to have it make it make sense. They
Yep.
try to do the integer chip thing make sense where you have
Yep.
to add in the zero pairs and like I get it. I get it. So I'm just going to suggest that subtracting a negative doesn't work well in context, which is the reason why we developed integers so late in our history. Like
Yeah.
they came very late in history, and making sense of subtracting negatives came super late in history. So we build some generalities about how we can kind of think about it from a number. If you remove something smaller than it, well, that's like what we did in second grade. Bam, the answer is going to be positive from that number. If you remove something bigger than it, oh no, now we're in debt. We're below sea level. We're below 0 degrees. Once we can make that generalization where kids actually understand, they're not just memorizing a rule, they actually understand that generalization, then they can look at a problem like -3 minus -5, and they can say, all right, how do those numbers relate? Well, bam, from -3, I'm subtracting something smaller than it, then the answer is going to be positive. And how far apart were they? They were 2. So the answer is positive 2. Yeah. Yes.
Yep.
So the upshot of today's episode is we need both meanings of subtraction. So if you teach younger students and you're teaching whole number addition and subtraction, please make sure that you have developed with kids that there are these two interpretations, two meanings, two ways of looking at subtraction. If you work with integers, do some of that work enough that kids can like understand that subtraction can have these two meanings. Help kids really understand integers, feel what's happening, be able to justify it, do it a lot. Don't go to rules, stay in reasoning. You're going to worry it's going to take too long. Let me tell you what happens when you just give them the rules. Then we have kids memorizing things like Pizza Steve and minus, minus, plus, plus. And then I'm in there working with kids and they see multiplication and they start doing minus, minus, plus, plus. And they see addition and subtraction and they start doing triangle Steve. And you're like, what is triangle Steve? See, I'm not even going to tell you because it's a memorizing thing that kids just look up and they misapply it and they stop thinking about stuff. I'm going to suggest if you have kids who are thinking and reasoning and confident that they can make sense of problems, they are going to A, do better on your high stakes tests because they go in confident. B, have their worlds open up to more math because they go in confident. That is our goal. They may not be as fast. You may not, quote unquote, cover as much stuff, but they're going to do it better and they're going to do it with confidence. And we need kids who have reason to fall back on. Woo! All right, y'all. Thank you for tuning in. Hey, what have we not done with integers that you still want to hear about? Let us know. We will develop some or devote some more future, some more future. Can I say more future podcasts?
Sure.
To integers. All right. Thank you for tuning in and teaching more and more real math. To find out more about the Math is Figureoutable movement, visit mathisfigureoutable.com. And thank you for spreading the word that math is figureoutable. Thank you for listening and making math more figureoutable.
To learn even more, make sure you register for our free challenge at mathisfigureoutable.com/challenge. You are not going to want to miss the evenings of May 15th through 17th, starting at 7 p.m. Central.
Math teaching, go register now. That's mathisfigureoutable.com/challenge. Join us to make math more and more figure outable. And if you can't join live, register and we'll send you access to the recordings. We'll see you there.